Hi, we are from the spatial indexing team. Um, our task was to implement a spatial index with respect to in-memory databases. Um, now let's look at what we had. We have traditional indexing structures like, say, B plus trees, quad trees, X trees, and KD trees, but none of them are more optimized with respect to in-memory databases or with respect to, say, points, rectangles, or polygonals, or roads, or any kind of geospatial data. So our task was given to us where we have to implement a geospatial indexing where we can efficiently index points or rectangles. And to progress with that, we considered PR QuadTree for indexing points and MxCif QuadTree for indexing rectangles. Um, an MxCF QuadTree for indexing rectangles. Our task also was to figure out ways where we can reduce the memory utilization, perform cache consciousness, and various other tasks which will improve an in-memory database. Now, let's look at a PR quadtree. A PR quadtree is a point region quadtree, which is based on using regions for quadrant divisions and using points with respect to those regions. So we divide a given parent quad node to four regions and insert points into the respective regions based on its location. So each quad node contains the region information and pointers to four child quad nodes. And all the leaf nodes contain a data point or are either empty. This is the algorithm written in provided by, to us by Dr. Hanan Samat. Um, now let's look at the implementation of the algorithm. Now, if you look at it, you have the point minus 70 comma 70 first inserted into the parent quad node. Upon the point 60 comma 60, or say minus 70 minus 70, we divide the quad node immediately into four quad nodes, and we proceed based on that. Now, if you look at the last point, that is the subfigure D, you have 60 and 25 comma 25. So even when a second data point comes in, we immediately divide the quad nodes. So what we observed here was we observed an advantage and a disadvantage with respect to it. So when you keep dividing the quad nodes, yes, we do have a we get a more pruned search. But the problem with this is it creates a large number of unnecessary quad nodes. Say you only have four data points, you're creating four quad nodes extra. So what we decided to do was we consider the quad nodes based on a leaf capacity. If a leaf capacity is given to us, we divided only the leaf capacity is increased a particular value. So, like I said, we only split the quad node once a quad node's leaf capacity has been reached. That capacity can be configured directly, say 4, 8, 16, 32, or whatever you wish based on your data size, your data, or how you would like your search and insertion time. Now I'll explain how the algorithm works. Now once minus 70 comma 17 inserted, nothing happens. 60 50, still nothing happens, as say you have the leaf capacity as 4. It has still not reached the total leaf capacity for a given quad node. Now minus 70 comma minus 70. Now once 20 minus 10 is inserted, we divide into all four regions, and then we assign the particular points into its respective quad nodes. Now if you look at it, when 10 comma 10 comes into the northwest quad node, we still don't divide it. The primary reason is even the children have the same kind of leaf capacity. So say we insert more number of quad nodes in this, more number of points in this, then even this quad node will split into four. The benefit of the benefit of the change of the algorithm is the number of subdivision reduces, the number of quad nodes reduces. So this results to lesser number of pointer chasing, and lesser memory occupied by each quad node. So if only you have 4 points, you only have one quad node. But in the previous algorithm, you have the root quad node plus additional four quad nodes. So like I told you, now since 4 points of them, northwest quad node also has been divided. Now, memory utilization reduction. So our algorithm reduces the memory utilization by making the leaf capacity a configurable parameter, and we subdivide based on the total number of points present in a particular quad node. We store all of these points in a particular vector collection, and we determine when to subdivide based on the collection size. So once the collection size has been reached, we then subdivide based on we then subdivide once a collection has been reached. Like I explained before, this reduces the memory allocation for each particular quad tree. Now, how we implement cache consciousness uh, is to now certain quad nodes or a particular quadrilla. Let's look at the main quadtree. It will have the root quad node, the children quad nodes. All these quad nodes will be accessed multiple number of times. So how do we make sure that the cache line is used very effectively? In the previous Hun and Summons implementation, you have a pointer to each particular child. So what happens is the memory stores each particular child in different locations. So we didn't want to do that. So what we did is took each child node, we took each node and put it in a particular vector collection. So all the nodes are represented in a collection, and so when it's allocated, all all the memory is allocated on one particular cache line on based on the cache line size. So one quad node will have all of its children and all of its bounding box data in one particular cache line instead of having to have it in different pointers. It will result in pointer chasing. So to achieve this, we placed all the pointers in a vector like I explained. Additionally, we remove a lot of unused variables, and we remove many variables and hard coded them to make sure we don't use additional variables in the stack. Now, what is the advantage of having this cache consciousness? One primary advantage is data locality. So once we have all the data assigned in the cache line, either we say update or do a delete operation, it removes all the data from that particular cache line immediately. In the previous implementation, you'll have references to other parts of the cache line. Now we don't have that. You have all your data reference in one particular cache line. So this improves the data locality for each quad node and its references. So this also improves application performance with respect to other applications. So say you have you have other application being loaded in the in memory. The memory utilization by our program is very good, as it only takes its allocated memory spot. Now, like just like how we done PR QuadTree, we have also implement MxCif QuadTree along with the same concept of dividing based on the leaf capacity. The only difference is instead of having points, we have boxes. So like this is the Dr. Anand Samat's algorithm, where you keep inserting the rectangles into particular quad nodes, and once it reaches say a size 2, we immediately split the quad node. Now this is our change implementation. Like now you have the first rectangle, second, third, fourth, and we immediately subdivide once we reach the leaf capacity, that is 4. Is similar to our PR QuadTree, but there's one particular extra challenge along with MxCF QuadTree is overflow rectangles, where let's say the rectangle is overflowing with respect to the bounding box. That is, let's say a rectangle is in this location, then we have to insert it into another collection called overflow rectangles, which I'll explain now. So yeah, the similar kind of memory utilization reduction happens with respect to PR and MxCif, as we reduce the number of nodes that is being created and store all the rectangles in another collection. We also store it in another collection of overflow rectangles. Basically, whatever rectangle is not able to fall into a particular quad node or quad node children is put in the parent quad nodes collection, and we search that, and the children nodes to determine if a particular rectangle is present or not. The same kind of cache conscious implemented in PR is also implemented in MxCif. Same goes to data locality. Now I'll explain our results. So if we can have a look, this is our results. How we've conducted our results is we considered a leaf capacity from 1 to 2048, and we found the memory usage using the top command. We've done three different runs, and we've determined the memory usage, the insertion time, and the search time. The insertion time is the total time taken to insert all the points. We've considered the DDS dataset as provided to us by Professor Sarwat for points and rectangles. Insert all the data. So once we insert data, we calculate the total time taken, and for search time, after we insert the particular point into a quad tree, we calculate how much time it takes to search that particular point, and we average it out 3 times, because we conduct a search we conduct 3 searches for each point. So that is the complete search time. So if you have a look, the average memory reduces significantly with respect to leaf capacity, but there is a problem with respect to considering a 2048 leaf capacity. If you can clearly have a look, it's a search time. The search time literally quadruples. Now if you look at it, it's 2400 milliseconds, but now if you look when you look at a 2048 leaf capacity, the search time is quadruple, because you're searching a whole collection of objects instead of going through a log-n search with respect to nodes. So to reduce your memory capacity and to have a good search and insertion time, it would be a good sweet spot to go with the 8/1632 leaf capacity. So you have a lesser memory and you have a good search time and insertion time. Now this is the thing for a PR quad tree. Next, if you look at PR quad without cache consciousness, you can notice there's a little bit increase in memory usage with respect to non-cache with cache conscious PR quad tree. This happens because we are, like essentially we explained, we are packing all the nodes into a collection. So because of this, this is actually decreasing our memory usage too. Now this is our MxCif quadtree with cache conscious implemented. This is the result that we have. If you notice here, also we have a huge search time increment with respect to the leaf capacity, and search time also quadruples with respect to the initial leaf capacity. So if you have leaf capacity 1, the search time is only 8,000, and once you come to 2004, it's 1,000. It is 14,000. There is an increment here also, but again here also, if you notice, you have a very good sweet spot with respect to 81632, where you have a memory usage of only say 7 MB and 6 MB, which is kind of in the same range with respect to leaf capacity 1. So this is our results. With respect to future work, or what lessons we learn from implementing this, is to that we should have a common base class or quad tree and quad node, and kind of extend from that for PR quad node and MxCF quad node. We remove many inheritance which is causing extra memory usage for the bounding box and the points. And then one important thing is to use a binary tree to calculate the overlapping rectangles instead of doing a linear search for the overlapping rectangles, and to use threads more for respect to search and query range, and support parallelism. Thank you.